Hello everyone. In this class, we are going to study some other important concepts of NMR spectroscopy, say the coupling constant. Before going to the coupling constant, we have to understand about proton counting. It is nothing but integration of protons in NMR spectra. Whenever you scan a molecule or any sample for NMR, you will get the NMR spectrum. Based on the NMR spectrum, you can detect how many types of protons are there in the molecule or how many different kinds of protons are there in the molecule. For that, the main thing is you have to count the protons. It is not easy to count 1, 2, 3 for the number of protons present in the molecule. Rather, you have to go for the integration method. Here in NMR, this is the typical NMR spectrum for this molecule. Here you will see that there are many peaks appearing in the NMR spectrum. The area under each peak in the NMR spectrum is proportional to the number of hydrogen atoms present in that particular environment. Say for example, here you will have a very big peak, here the half peak, here half to that peak, and here is the smallest peak. That means to say height of the peak decides the number of protons present in that particular type of environment. Say for example, here for this molecule, consider these two methyl groups as A, this as B, this methylene as C, and OH as D. Because there are 6 protons, the height of the peak should be eventually very high. That's why it is showing very high intensity in the NMR spectrum. Followed by this is the B proton, that is another methyl. Here there are 6 protons, here there are only 3 protons. Hence, you can expect the size of the peak to be half of the big peak. Exactly this peak, this B peak is half of the A peak. Coming to CH2, CH2 has got 1 proton short to that of the methyl group, and hence it is half of the peak B, and the C is appearing at half. The last one is the OH, that is hydroxyl or alcoholic group, which is D proton. It is having only 1 H, and hence it is showing the very short peak. So based on the height of the peak, you can decide how many number of protons are there. This NMR spectrum clearly tells us that this proton, this peak, it shows that it has got largest number of protons, and the smallest peak refers to the molecule or the group or an atom having the smallest number of protons. So this is done by using what is known as instrument integration. The instrument itself will integrate the peaks. When you integrate the peaks, it appears as S shape. You can clearly see the S shape. The S shape indicates the integration. Once you do the integration, the number of protons are automatically shown on the NMR spectrum. Here you can see there are 6 spaces in total. The width between this is 3, this is 1.5, this is 1, and this is 0.5. It is the multiple of 2. This is how we can count the number of protons. Once we have understood the proton counting or integration of protons in NMR spectra, now we have to move to the important concept of NMR spectroscopy, that is spin-spin coupling or spin-spin splitting in 1H NMR. Before we go for this, we have to consider a basic molecule, that is ethanol. Ethanol is CH3, CH2, OH. When the ethanol was taken and ran the NMR spectrum, it showed 2 kinds of peaks. This methyl group, it showed a triplet with the relative areas of 1:2:1, whereas this methylene group, it showed a quartet of the relative areas of 1:3:3:1. And the peaks, the distance between the individual peaks in the multiplets is called the coupling constant. It is usually referred by the letter J, and it is expressed in hertz, and the value of coupling constant always fall between 0 to 18 hertz. In this slide, you will particularly understand and clearly understand what you mean by J. Here, these are the peaks obtained for the ethanol or ethyl alcohol. This is CH3 peak, it is showing 3 peaks. This is CH2, it is showing 4 peaks, and the relative intensity is 1:2:1 and 1:3:3:1 respectively. When you zoom this peaks, you will see an enlarged form of the peaks, wherein the distance between the 2 individual peaks, the distance between these 2 peaks is J, distance between these 2 peaks is J, distance between these 2 peaks is J, and this J is what is known as coupling constant, and the distance will always remain the same between these peaks. Here we have seen for these 4 peaks. If you zoom these 3 peaks, Here also the distance will be the one and the same. The distance between these two will be same. Distance between these two will also be the same, and it is represented by J. Then what do you mean by coupling constant, and how the peaks are going to be splitted and how the peaks are going to be coupled here, that we have to see. It is mainly seen by the fact that the magnetic field experienced by the protons of one group is influenced by the spin arrangements of the protons of adjacent group. We will clearly explain this by taking the example of impure ethanol. When you take impure ethanol, that is CH3CH2OH with some impurity, now the scientists for the first time observed that this CH3 peak is giving a triplet, whereas this methylene group or CH2 group, it is showing a quartet. Now you may be wondering, okay, this is having 3 hydrogens, that's why it is giving 3 peaks, whereas this is having only 2 hydrogens, but still it is giving 4 peaks. And this terminology 3 peaks, we don't call it as 3 peaks, rather we call it as triplet, and we call it as quartet 4, triplet 3. We will see this in detail in a short while from now. Before that, we have to understand why this methyl is giving a triplet and this methylene is giving a quartet. Now we have to clearly understand that these protons are influenced by these protons are influenced by these protons. So the magnetic field of this proton is influenced by the spin arrangement of this proton. The magnetic field of this proton is influenced by the spin arrangement of this proton. And you will see that the distance between these two always remains the same. And for methanol it is 7. The coupling constant is 7. That is the distance between the individual peaks in the multiplet. If there are more than 2 peaks in a spectrum, it is called as multiplet. Multi refers to many. We will see what can be derived by using the 1H NMR spectrum of impure ethanol. 3 important rules can be derived about spin-spin splitting in 1H NMR using the ethanol spectrum. Say for example, this is methyl chloride. Here all the hydrogens are present in the same atmosphere, and hence we say that these are chemically equivalent protons, and these chemically equivalent protons, they do not exhibit spin-spin splitting or spin-spin coupling. First, the 2 protons which are present nearby each other, they should couple, they should interact. Here coupling refers to interaction, magnetic field interaction. The magnetic field, it sends information from one proton to another proton, by means of which they will interact with each other. Once the magnetic field interacts with each other, the spin arrangement gets changed. Here all the 3 protons are present in the same environment, and hence we say that there is no coupling. Coming to dichloroethane, even in this compound, the 2 hydrogens on this carbon, they are having the same chemical environment, and hence no coupling. Always you have to remember that the equivalent protons may be on the same carbon or on the different carbons, they still do not couple. Instead you will get a singlet in the 1H NMR spectrum. The second rule that we can derive is a proton having n equivalent neighboring protons will give a signal and split into n+1 peaks with coupling constant J. What is that n+1 rule here? Say for example, consider carbon 1. The carbon 1 is having the carbon 2. This carbon 2 is attached with 1 proton. That means this proton is having the neighboring another 1 proton. So n+1, n refers to number of neighboring protons. This side it does not have any proton, but this side it has got proton. So n is 1 here, 1 + 1 is 2. That means this proton is going to give doublet, this proton is also going to give a doublet. So they both will couple with each other, because imagine that these 2 protons are present in the different atmosphere. This is the case if the hydrogens are present as neighbors. What if hydrogens are present are not as neighbors? That means these 2 hydrogens are separated by a carbon. When 2 hydrogens are separated by a carbon, no coupling takes place. If at all coupling wants to take place, there should be a pi bond here in this system. If at all there is pi bond, then the pi bond acts as a transmitter of the magnetic information from one carbon to another carbon, and hence the coupling takes place. Since here in this molecule there is no carbon double bond, you cannot expect any kind of coupling, because 2 protons are separated by 1 carbon. This is the second rule. And we can see some of the common multiplicities. This table, the first column refers to number of equivalent adjacent protons. The second column is type of multiplet observed. The third column is ratio of intensities. If there is no neighboring proton, then the multiplet will be a singlet in the NMR spectrum, and the ratio of intensity is just 1 because there is only one peak. The ratio can be only 1. Next, if there is a neighboring one proton, so n plus 1 rule holds good here. N plus 1, 1 plus 1, it will be 2. So you're going to call it as a doublet, and both the peaks will be having the same intensity. That's why we say that ratio will be 1:1. If there are two hydrogens on the neighbor, then 2 plus 1, it is going to be 3. It is triplet. The intensity is 1:2:1 ratio. If there are three neighboring protons, 3 plus 1, 4, that is quartet, then the ratio of the intensities will be 1:3:3:1. This refers to these two middle peaks will be having very high intensity, whereas the flanking peaks will be having very low intensity. If there are 4 neighboring protons in the molecule, then 4 plus 1 is 5. We call it as quintet, and the ratio will be 1:4:6:4:1. Finally, if there are 6 protons, then it will be 6 plus 1, 7. It is called septet. Then the ratio will be 1:6:15:20:15:6:1. This is called Pascal triangle. The ratio of intensities always they refer to Pascal triangle. This is about the common spin multiplicities that we encounter in NMR spectroscopy. If there is more than 2 peaks in an NMR spectrum, you call it as a multiplet. That means one peak should have been divided into more than 2. If there are number of singlet, then you cannot call it as multiplet. If the single peak is splitted into doublet, triplet, quartet, more than 3, more than 4, usually we refer to it as multiplets. Then the last and the third rule that you can derive from 1H NMR of impure ethanol is that whenever the two protons couple with each other, they should have the same coupling constant, that is J. If the two neighboring protons are coupling, that means they both should have the same coupling constant, because the distance between the two peaks, it remains the same between the two groups of protons. These are the 3 important rules that you can derive from the 1H NMR spectrum of the impure ethanol. Based on this, so far lakhs and crores of molecules have been structurally diagnosed. Now we have to deal in detail with the coupling constant. What is coupling constant? As we have seen, that coupling constant is a measure of the coupling interaction between the nucleus. It is the distance between the two individual peaks in a multiplet. So the spacing between the lines with a multiplet always remains the constant. It is usually denoted by J, expressed in Hertz, and it is a function of several factors. We will see which are those factors which govern the coupling constant. The first one is the nature of bond separating nuclei. Now we will take the example of this benzene attached with some groups. X here does not refer to any halogens. Imagine X is any alkyl, aryl, or any other functional group. Okay, this hydrogen here now it becomes ortho to this group. So J ortho, that is coupling constant for this ortho hydrogen, it will always be high, because the distance between these two groups is very, very less. So smaller the distance between the protons or the groups, more will be the coupling constant. Hence you will expect 6 to 10 Hertz of the J value. Next, coming to meta hydrogen, to this X, this H becomes meta, and as the distance is increasing, the interaction becomes less and less. Because of the less interaction, the J also becomes less. When compared to ortho, it is just 1 to 3, whereas ortho proton, it showed 6 to 10. The last is the para. With respect to X, this hydrogen is para. So J para, the distance, look at this distance, it is very, very far. When the distance becomes very, very far, the interaction becomes very, very less. Because of the smaller interaction, J sometimes becomes 0, or if at all there is any small interaction, it may show very, very small coupling constant value. This can be best understood by taking this example. This is 2,4 dinitrophenol. Here there are 3 kinds of protons: orthoproton, metaproton, and this is also metaproton. Now we have to check the distance and the coupling constant value that we are going to get here. For J, AB. That means the coupling constant between these two, it is very small, very small, because the distance is quite large. With respect to this, this is meta. Always for meta, the coupling constant value will be intermediate, hence you are getting only 2.8 hertz. Whereas the JBC, because these two are neighbors, there will be more interaction. We know that more interaction, lesser space, J will be always high. Compared to JAB, JBC will be showing very high coupling constant, indicating that these two protons are nearby each other and they both will couple with each other. Why they both are coupling? Because they are coupling since they both are present in the different atmosphere. For this hydrogen C, what is the neighboring group? Phenol. What for this proton, that is proton B, what is the neighbor? Nitro. That means for this hydrogen, nitro is the neighbor. For this hydrogen, phenol is the neighbor. That means these two protons are having different neighbors. Different neighbors means non-equivalent protons. Non-equivalent protons means always they couple with each other. This is the first factor that governs coupling constant. The second one is the long range coupling. If the two hydrogens are separated by more than 3 bonds, then usually we observe very small coupling. But if at all there is a pi bond between these 3 carbon atoms, then there will be very effective transmitter of magnetic information, as it is proved to be the pi electrons are involved in this. So usually the unsaturated system will involve long range coupling. The last and the third factor which governs the coupling constant is stereochemistry of the molecule. Whenever we say stereochemistry, we know that the arrangement of groups will be in different direction. So as soon as you say stereochemistry, two parameters that comes to our mind is cis and trans. So this is cis alkene and this is trans alkene. Always trans alkene will have higher coupling constant when compared to cis alkene. We will see just now. And another stereochemical factor that we have to consider is axial and equatorial. Always JAE. That means if the two protons, among the two protons, one is axial, another one is equatorial, then such kind of protons will have more interaction. Eventually, they will show more coupling constant. This is followed by equatorial, and the least will be the axial. This axial will be orthogonal to each other, and hence they will show very small coupling, whereas equatorial they show orthogonal, whereas AE shows this EE shows syncoplanar, whereas AE shows antiperiplanar. We will see all this in a short while from now. So now we are going to see some coupling constant value for different types of system that we encounter. Here you have to remember two important words, geminal and vicinal. What is geminal? If the two protons are present on the same carbon atom. See here, these two protons are present on the same carbon atom. Such protons are called geminal. If such is the case, then the J value will be very high. It is of the order of 12 to 15. So always J gem, coupling constant for the geminal protons will always be having very high coupling constant value compared to vicinal proton. Vicinal refers to different carbon. See here, there are two protons, no doubt, but two protons are attached to different carbon atoms, whereas in this case, two protons are attached to the single carbon atom. That's why it is referred as geminal and this is vicinal. Why it is showing very less J value? It is because of the free rotation between these two bonds, between these two carbon atoms. Whenever there is free rotation, the interaction becomes less. When the interaction becomes less, automatically the J value also becomes very less. As I said, J trans, these two hydrogens are on opposite sides and hence I call it as trans. The coupling constant for this J trans will be very high because this trans bond involves the bond angle of 180 degrees. Why cis will always show very less coupling constant value? Because here the bond angle is 0. There will be less interaction. Here there will be more interaction. Then J for ortho, meta and para. With respect to this, these protons become ortho, this is meta and this is para. Obviously, always for ortho, you get more coupling constant, meta, intermediate, whereas para, it is nil, or if at all it is present, it is very less. There are two important factors which influence the coupling constant or which affect the coupling constant. As we have already seen, they are geminal coupling and vicinal coupling. Geminal coupling, J, it is referred as J superscript 2, whereas vicinal coupling, it is referred to as J superscript 3. Why 2? because here the coupling interaction between two non-equivalent protons on the same carbon, they are separated by two bonds. Here two protons are attached to the same carbon atom and hence the name geminal, and these two protons are separated by two bonds and hence the superscript 2 here. Here the coupling constant is designated as J-gem or J2HH dash. Why I say HH dash? Because both the protons should be in the different chemical environment. Rather, I will say that these two are non-equivalent protons. The coupling constant range for geminal coupling is between minus 20 Hertz to 44 Hertz. Coming to vicinal coupling, it is represented as J3 because here the two protons are separated by three bonds, 1, 2 and 3. And because it is separated by three bonds, it is represented as J superscript 3. Here the coupling interaction will be between the two non-equivalent protons separated by three bonds on the adjacent carbon. Here same carbon, but here it is adjacent carbon. The coupling constant here it is represented as J Wick. Wick refers to vicinal, or you can represent it as J superscript 3 subscript HH dash, because here both the hydrogens are present in different chemical environment. The coupling constant range for the vicinal coupling will be between 0 to 12 Hertz. So obviously you can see that for geminal coupling you will have very large range, whereas for vicinal coupling you will have very short range. Having defined geminal coupling and vicinal coupling, next we move on to factors influencing particularly vicinal coupling and the stereo structure, and this was best explained by the famous scientist Karplus. He has given a graphical representation and it is in the form of a curve, and hence in the honor of him they have named it as Karplus curve. What is Karplus curve? It is the representation, or it is the relationship between coupling constant and the dihedral angle. We are encountering a new word, dihedral angle. What is that? How to define dihedral angle? It is the angle subtended between two planes. We will see when we go for the graphical representation. But we will now see here the magnitude of JHH dash between vicinal protons. Coupling curve, Karplus curve, it is always for the vicinal protons. It is mainly influenced by the dihedral angle theta between the vicinal protons. That means these protons are present in different angles or different planes. So that plane is represented by theta. Theta is nothing but dihedral angle. Usually coupling is mediated by the interaction of orbitals between the bonding framework. As I said earlier, if the two protons are coupling, that means the two protons are interacting. What is interacting? The orbitals of the protons are interacting. The magnetic field of one proton, it is influencing the spin arrangement of the another proton. It is because of that coupling takes place. Because of the coupling, splitting takes place. The magnitude of vicinal coupling thus depends on the overlap of the orbitals, and hence we can see that there is a relative orientation of the coupled nuclei in space, that is the theta dihedral angle. So Karplus not only he gave a curve, he also gave two equations. Those two equations are called Karplus equations. We will see here. So these two are the equations. J3HH dash, it is nothing but vicinal coupling. The first one equation is 10 cos square theta in terms of 0 degree less than or equal to theta less than or equal to 90 degrees. And another equation that was given by Karplus is vicinal coupling J3HH dash is equal to 16 cos square theta, wherein 90 degree is less than or equal to theta or less than or equal to 180 degree. For 10 cos square theta, the range is between 0 to 90 degree. For 16 cos square theta, the range is between 90 to 180 degree. That means for the Karplus equations or the Karplus curve, we consider the range from 0 degrees to 180 degrees. That is, theta will be in the range of 0 to 180 degree. So these two are called Karplus equations, and this is the Karplus curve. What is the Karplus curve? It is the graphical representation in which theta is plotted on the x-axis and coupling constant is plotted on the y-axis. We got a curve like this, and what does this curve says? Here you will see that this is the maxima of the curve, and this is slightly lower than the maxima, and this is the minima of the curve. You can see that the two protons are there, HH dash. Both the protons are present in different planes. You can refer to it as open book structure. So the difference between these two angles, these two planes is called theta, that is dihedral angle. So Karplus curve, it is the relationship between dihedral angle theta and coupling constant J. So how do we define or how do we explain this Karplus curve? When J, that is coupling constant, reaches maximum when theta is 180 degrees. See, this is coupling constant. It is almost 13 here now. Now 13 is the maximum. When it is 13, that is coupling constant is maximum, the theta will be 180 degree. Slightly to maximum, if the value of coupling constant is slightly smaller than the maximum, that is in this case say it is 11, then the theta will be 0 degree. Here in this case, whenever it is a maxima, then it refers to anti-periplanar structure. In the anti-periplanar structure, there will be more interaction. Here there will be overlap. The best overlap of the orbitals takes place at higher J value. That means more interaction will be there. That's why it is giving higher J value that takes place whenever there is 180 degree theta. Whenever it is 0 degree theta, it will be slightly lesser than the maximum. The J value falls down. In this case, almost it is 2. We can say nil when the theta is 90 degree. That means whenever the theta dihedral angle is in the midpoint, then it reaches a minimum. This is the explanation of Karplus curve. It mainly gives the relationship between coupling constant J and dihedral angle theta. To illustrate this best, we have taken different examples here. This is the chair form of cyclohexane, but OH is attached, so it is cyclohexanol. We know that cyclohexane has got two types of hydrogens. One is axial hydrogen, another one is equatorial. This is axial, this is equatorial. Here alcoholic group is in the axial position, whereas hydrogen is in the equatorial. This is another CH2 represented as A and E dash. Here there will be very less interaction between E dash because of the orthogonal or syncoplanar. We say that's why it is having very less coupling constant. Whereas JAE, the interaction between these two will be very high when compared to JEE dash, because hence it is showing the coupling constant of 3 Hertz. So this is at 60 degree. Now we will see that this hydrogen which was present in axial position, now it is coming to equatorial position. Now what best you can expect? This AA dash, JAA dash, because of the anti-periplanar structure, the overlapping will be the best here. That's why you can expect more J value. Look at the J value, it is 11.1 Hertz. The theta is 180 degree. And JAE, again it is very less when compared to JAA dash. The second one, here it is the Newman structure. The Newman structure, it has got 2 hydrogens. The distance between the 2 hydrogens is 60 degrees. If it is very 60 degrees, very small, then that means it is syncoplanar. The interaction will be less. Eventually the J also will be less. So it is 3 to 5 Hertz. The theta is 60 degree. On the other hand, when they are anti-periplanar, both the hydrogens are on the opposite side, the interaction will be the best, which eventually leads to higher coupling constant value. Here the theta value will be 180 degree. This best explains the Karplus curve, that is the relationship between J and theta. Another example that we can take here to illustrate coupling constant is between cis and trans isomers. This is the cis isomer. Here theta is 0, that is bond angle is 0. J will be obviously quite less. It is, the range is 5 to 14 Hertz. Whereas in the trans isomer, the dihedral angle is maximum, that is 180 degrees. And hence the J value will be 11 to 19 Hertz. The last aspect for today's class is the instrumentation, that is NMR spectrometer. This is the typical sketch of a NMR spectrometer. Usually NMR is scanned by means of continuous wave method, and hence this spectrometer is called as continuous wave spectrometer. Here you have to understand that this is the glass tube or the sample tube. This is made of glass and the thickness of the wall will be just 5 millimeter. Inside this, we put the solvent, we put the sample, and then we dissolve the sample in the solvent, and then we keep it in the NMR by capping that glass tube. Once we place this glass tube, the sample tube, in between the poles of the magnet, you know that NMR mainly deals with the change in the spin state of the magnetic field. So whenever you place the sample in between the magnetic poles, the molecules, the nuclei present in the molecules, it will orient itself. Now I'm going to supply the energy supplied in the form of radio frequency energy, or it is transmitted through radio frequency transmitter. It is shown in red color. These are the coils of radio frequency energy, and this radio frequency transmitter, it is always received and amplified. That means you can control the flow of energy, you can control the flow of frequency to the sample. Once the sample which are oriented and you give the energy, they get excited. Here in NMR we say that spin flipping. After spin flipping, the two important processes takes place: saturation and relaxation. After the relaxation, the molecules, it will show different kinds of protons in the form of NMR spectrum, which is controlled and recorded in the monitor. In the monitor, you can see the NMR spectrum, which is the plot of chemical shift on x-axis and relative intensity on the y-axis. This is the typical diagram of the NMR spectrometer.